This lesson focuses on area and surface area. In many of the problems today, you will also see the use of Pythagorean theorem, Pythagorean triplets, and simplifying square roots. This first warm-up is asking us to find the area of a circle inscribed in this triangle. Many of you will recall that when we did geometric constructions, we worked on inscribing circles and triangles. And when we did that, we also discussed properties that appeared with regularity. One of the things that we learned was in an equilateral triangle, and for that matter in any triangle, the medians intersect at the center of the circle. So those are roughly about medians. They're not constructed, but where those medians intersect, we have the center of the circle. And in order to find the area of the circle, we need to figure out the radius. The other thing that we learned is that center of the circle was 1/3 of the distance from the base to the vertex. In other words, that radius is half the length of this piece of the triangle. And you can think about that just with some logical reasoning. From here to here is another radius. And what we learned with constructions and measurement is from here to here, there was another radius. So in solving some problems, that's a useful relationship. In this first problem, we're interested in finding just the radius, and then we're going to look at why we might use the other piece. In fact, one way to begin this problem is to consider this right triangle. If I bring this right triangle out, I know that this is 6, and since it's an equilateral triangle, this is a right angle and this is 3. I need the height of this triangle, because if I find the height of this triangle, I can divide it into 3 parts to get the radius. So by Pythagorean theorem, I know h squared plus 3 squared is equal to 6 squared. So working that out, h squared plus 9 equals 36. Subtracting 9 from both sides gives me h squared is equal to 27. Taking the square root of both sides, solving for h, I get h is equal to the square root of 9 times the square root of 3, and the square root of 9 is 3, so h is 3 square roots of 3. Since h is 3 square roots of 3, going back to that property that I opened up with, this is a 2-to-1 ratio. So I'm going to take 3 square roots of 3, divide it into 3 pieces, and that's what r is. So r is just the square root of 3. So the area of the circle is pi times the radius squared, which is pi times the square root of 3 squared, which is 3 pi, and our units are centimeters squared. The second thing that we talked about, I'm going to clone the page here, is what if a different question was asked of you, and you had to find not the area of the circle, but the shaded region between the circle and the triangle. So this blue region that I'm creating. We're going to keep the learning from the previous page. And in fact, we can look at them side by side. And think about, in order to solve this problem, I need to find the area of the triangle and subtract out the area of the circle. So the area of the circle, as we know, is 3 pi. To find the area of the triangle, we need the entire height, which is 3 square roots of 3, and we have the base to be 6. Triangle area is 1/2 the base, 1/2 of 6, times the height. In keeping with efficiency, we want to reduce along the way. So 2 goes into 6 3 times. The area of the triangle is 9 square roots of 3. If I subtract out the circle, that's the shaded area. And the units would be centimeters squared. The next thing we did was focus on surface area, which is just area of a solid, but really it's still a two-dimensional problem because every solid can be folded out into a net. Or you can think of this particular solid as 4 triangles and a square. And it's a square base because it's 10 by 10. So we need to figure out the area of the square, which is easy. 10 by 10 is 100. But then we need to figure out the area of the triangles and multiply that by 4. And since the base is a square, all 4 triangles are congruent. So the 13 correlates to this edge length, and all of the edges are the same. So if you just think about this picture in 3D, it always looks a little distorted, but it's an isosceles triangle with an edge length of 13. So it also has a base of 10. Because the edge length is 13, we need the height to figure out the area of that triangle. And this right here, if you focus in on just this right here, that is the first triangle, I guess, that we've seen in this video. That's a Pythagorean triplet. Because this is 13, and since the base is 10, that is 5. Since it's a right triangle, that's one of the Pythagorean triplets. It's a 5, 12, 13. So, to figure out the final area, we would say 100 plus 4 times half the base times the height. And focusing on efficiency, we want to reduce along the way. So we have 100 plus 4 times 60. So 100 plus 240. that sums to 340 square units. And that's the surface area. So you'll see I have this note here, be able to find h. Sometimes the book gives you that, but I also know that we're familiar with Pythagorean theorem already. So you need to be able to use Pythagorean theorem even if that height isn't given to you. The next example is the surface area of this regular hexagonal prism. Some of the similarities are that it's a 3D picture, but surface area is really about adding up all the flat surfaces. And another similarity is that it's a regular polygon, so you're going to use Pythagorean theorem again. And I'll show you how that appears. First, the simple part is there's 6 rectangular sides, or faces, 10 by 20. So 6 times 200. And then there is 2 hexagons. So the hexagons are regular. And from the diagram, this length of 10 appears there, and the radius of the hexagon is also 10, because a hexagon is divided into 6 equilateral triangles. That's a little bit off, but as for the sketch, I think it's just best to keep it clean, and keep in mind there's 6 equilateral triangles. So this is 10, and this is 10, and this is 10. In order to find the area of one triangle, we need to find the apothem of that hexagon, which is also the height of that triangle. So, focusing in on this right triangle, and then pulling it out of the picture, this is 10, this is 5, and we need the apothem, so we're going to use Pythagorean theorem to do that. To keep moving things around here. So I know that a squared, because this is a right triangle, plus 25 is equal to 100. So a squared is equal to 75. So the square root of both sides gives me a is equal to, and 75 breaks down to 25 and 3. So a is equal to the square root of 25 times the square root of 3, or 5 square roots of 3. So I'm ready to finish the problem. 6 rectangles, each having an area of 200, plus 2 hexagons, and each hexagon has 6 triangles, and the area of the triangle is 1/2 the base times the height, or also the apothem. So that represents the area of one triangle. Stick with the efficiency. 2 goes into 10 5 times. So we have 1,200 plus 2, and then 6 times 5 is 30, times 5 times the square root of 3. So that's 1,200 plus 2 times 150 root 3. Scrolling down just a bit, that gives us 1,200 plus 300 square root of 3. That's the final answer. because those are not considered like terms. So squared inches. Let's just kind of zoom out. It's a pretty big problem. Lots of things to think about. Calculations are still pretty simple. You do need to know how to do Pythagorean theorem. I think drawing pictures to start the problem is a really good strategy to keep your work meaningful.